So let's just get the slideshow up real quick. Whenever Google Slides finishes, I can share my screen and then we can start. There we go. Share screen. All right. Welcome to Chapter 15, Glaciers and Glaciation for Geology at Gilbert Community College. Obviously, in this chapter, we're going to talk about glaciers and glaciation. So, what is a glacier? A glacier is a thick mass of moving ice that forms over hundreds to thousands of years by accumulation, compaction, and recrystallization of snow. Glaciers are part of two basic cycles, the hydrologic cycle, the water part, right? And the rock cycle as an erosional depositional agent. Glaciers exist on land. That's how you distinguish them from, let's say, icebergs, right? There are different types of glaciers. For example, there's valley or alpine glaciers, which are glaciers that are in valleys of mountainous areas, such as the one shown here. This is a flow down the valley and glaciers traveling downhill. Nope, went the wrong way. There we go. And secondly, we have ice sheets. Ice sheets are very large scale compared to valley glaciers. Greenland and Antarctica would be examples of ice sheets as opposed to valley glaciers. And these, the ice flows out in all directions from the snow accumulation centers. You could consider these the continental-sized ones, right? So let's talk ice sheets versus ice shelves. Along the outer parts of Antarctica, glacial ice flows into the sea, creating ice shelves. In shallow water, the ice can touch the bottom and is grounded, but in deeper water, the ice shelf itself floats. The thickest of landward side and the thin is seaward side. Some ice shelves are unstable and can break apart. Naturally, this is, again, where icebergs come from. And the breakup of these ice shelves could attribute to regional global warming and climate change. Here's an image showing kind of what we're talking about here. So you have, again, this could be Antarctica, for example. As you get closer and closer to the water, the ice layer thins in size, creating an ice sheet. And then eventually those giant ice sheets break off, creating your icebergs, which then float around and take down Titanic and stuff like that. Image shown here from January to March of an ice shelf forming. You can see the after picture has this gigantic amount of ice that wasn't there before. And of course, as I said, these things crack off, they break off, what have you. The Larsen Sea ice shelf in Wales has an example of this. Oh, sorry, not in Wales, in Antarctica. Wales for size comparison, my bad. And you can see how large these shelves are compared to a country, right? A very large thing such as Wales. And you can see this ice shelf slowly cracking. These colored lines indicate how far the crack has gone because this ice shelf is eventually going to break off into an iceberg. During the Ice Age, we had, well, ice sheets. That's where the Ice Age term comes from. For the past 2.6 million years, ice sheets have advanced and retreated multiple times, especially in the northern hemisphere. About 18,000 years ago, ice sheets covered large portions of North America, Europe, and Siberia. If you've seen pictures of the Ice Age, you know what we're talking about here, right? The Arctic Ocean is covered with sea ice, frozen seawater. That's different from glacial ice. Just keep that. I'm sure you can figure out why that is, right? Sea ice, seawater. Sea ice is about up to 4 meters thick, so pretty thick nonetheless, right? Whereas glaciers can be hundreds to thousands of meters thick. Glaciers form where snow falls in winter, then melts during the summer, right? Glacial ice formation occurs, 1, through snowfall, including lots of air and small flakes. 2, snowflakes becoming smaller, thicker, and more spherical. 3, forcing the air out. And then 4, the snow is recrystallized into dense mass and small grains that we call firn. So the snow falls, compacts. That's how you get your glacier. So a glacier isn't just the snow that you are used to in your winters. It is highly compacted, thick, quality Not ice, but comparable. Once the thickness of the ice and snow exceeds 50 meters, firn fuses into a solid mass into like ice crystals, giving you a glacier. What I just said, right? Here's an example of this, right? That's not just, you can't go pick a snowball out of that ice sheet, for example, or this glacier. It looks glacial to me. Yeah, it's on the land. It looks glacial, and as you can see, it's gigantic. These take usually quite a fair amount of time to actually form. And again, this isn't just all this snow compacted and fell at one time. This is years and years and years of compaction of this product. So, we talked about what glaciers are. Let's talk about how they move. First thing we talk about is plastic flow, the movement within ice under pressure. This happens below depth of 50 meters, where the ice behaves as sort of a plastic material, a ductile, not breaking material. The meltwater acts as a lubricant at the base of the glacier and moves it around. Above 50 meters, we have a brittle zone where instead of the glacier having some plasticity to it, it just fractures and cracks, right? This is where you get your crevices from, things of that nature. Crevices are present in the zone of fracture, but sealed off by plastic flow at depth, right? If it's not brittle, it's not going to fracture and crevice. And here is an image, a cartoon to show this idea. Ice in the zone of fracture is carried along piggyback style, essentially. The zone of fracture can be that 50 meter, somewhat around 50 meter distance spread. Below 50 meters, ice behaves more plasticky. It will move without breaking and gradually flows, essentially like a fluid, right? Basal slip occurs episodically. Ice in contact with the valley floor remains fixed, more or less, as stress builds at the point where the glacier lurches forward. So the ice at the bedrock isn't moving, and then the middle part, that real thick middle part of the ice is flowing, which is where that curved line comes in. So the iceberg is sort of rolling on top of itself, if you will, and that's where you get your movement from. So the iceberg doesn't just slide across the bedrock as one giant chunk, for example. There's an example of a crevice and a very brave man walking through it. So, rate of glacial movement. How fast does the glacier move? Well, like a river, glacial ice does not all move at the same rate. Flow is fastest at the center of the glacier. The velocity ranges from extremely slow to several meters per day. So, glaciers can move really fast or not very fast at all. Some glaciers exhibit extremely rapid movements, and these are called surges, where it surges forward, right? We can look at this glacier in Switzerland here, where in 1874, they staked out the position of the glacier, and then you can see over time how the glacier moved and the way it moves. So over the course of, what'd that be, 8 years, the glacier slowly moved forward, but moved forward in, again, sort of like a river, where the center of the river is fastest because there's less friction from the rocks, and the edges move slower. And you see down here at the bottom, the terminus crept forward more or less along path with those stakes. We talked about different zones with rivers. Now we can talk about different zones with glaciers. First of all, you have your zone of accumulation. This is the area where the glacier forms, right? Located above the snow line, and it's where you get your snow. Then you have zone of wastage. This is the area where there is net loss of glacial ice from melting or calving or something like that. So snow forms above the snow line, slowly moves downhill because, right, elevation, it gets colder, you get snow line at elevation. Once you pass that snow line, then you have the zone of wastage where things melt, and eventually you get your streams that feed your tributaries that feed your rivers that are part of the hydrologic cycle. Here is another fracturing event going on with a glacier. That gigantic piece of ice is going to float around for a while, eventually give yourself an iceberg. Glacial growth is greater, if it's greater than melting, then an ice front advances, a gigantic big chunk of ice moving along. However, if glacial melting is faster, then the ice front retreats. So it all depends on, as we can see here, 1941, 2004, Glacial melting was stronger than the growth, so the glacier essentially contracted or rescinded in on itself. Glaciers are capable of lots of erosion and sedimentary transport, right? As we talked about before, these are gigantic chunks of ice, and they kind of do what they want. Glaciers erode primarily in two ways, either plucking or abrasion. Plucking is when the glacier flows over bedrock, loosening and lifting up blocks of material. Abrasion occurs, essentially, as the name implies, when a glacier acts like sandpaper to smooth and polish a rock surface. Glacier abrasion, the sandpaper one, produces rock flour or pulverized rock, and glacial striations or grooves, cuts in bedrock. Glacier erosion is controlled by how fast the glacier is moving, how thick it is, the type of rock fragments that are caught up in the glacier, and of course the erodibility of the surface below the glacier. Stronger the material, less likely it is to be eroded. Here we can see these scratch marks, if you will, from the glacial abrasion. If you live up in the Upper Peninsula around the campuses of really either Gogebic or its satellite campus in Houghton, these are rather common occurrences. If it looks like a rock's been kind of scratched and beat up a bit by something, a glacier did that. Glacier Lake in New Zealand with rock flour. Again, if you look around that lake, what do you see? Very fine powdery material. That's because the glacier rubbed it all up and powderized the original rock that was there. Landforms created by glacial erosion. Landforms, as I said, due to how the glacier works, it's pushing, it's shoving, it's cutting, it's grinding, what have you, you can create topography. Valley glaciers create shock angular topography, and ice sheets subdue or clean out most of the topography. So we have a V-shaped valley and unglaciated topography. As time goes by, a glacier comes down into that valley. And what happens? The glacier, when it then recedes, creates this large glacial trough, as shown in C, down below, and essentially took the rather sharp cut of the river in the unglaciated part and narrowed everything out. We can see a lot of vocabulary words in these images: Arte, ton, horn, cirques. I don't really know how to pronounce that C one, sorry. And these are all due to the massive force of the push of the ice of the glacier. So, glaciated valleys. These are when glaciers widen and deepen the valleys, created U-shaped glaciers as shown before. And you have hanging valleys, which are the tributary valleys to the main valley, where the glaciers in the main valley eroded deeper than the tributary glacier. Again, why does this have this nice U-shaped curvature to it? Because a glacier cut through it, not a river. If you look at canyons and stuff like that were river cut, they don't look this way. That's how we can tell what created what. And here you have your hanging valley, wherein the glacier didn't cut deep enough to, let's say, hit this water down below, but it did cut as deep as it cut, right? Giving you this waterfall effect. This is, again, we can tell a glacier because of the U shape, the soft shape of the valley as opposed to a rigider shape, and the fact that this water didn't have time to erode all the way down to the lake bed says it was glacier formed. Cirque, I'm sorry, I don't know how to pronounce that. A bowl-shaped depression typically found at the head of a glacial valley. Right, the glacier needs to start someplace. This would be the head. This would be where the glacier started. The glacier moved in one direction, and that direction is shown by the shape of this topography. Glaciers once surrounded this mountaintop, eroding the sides, melting, and leaving a peak. That's why the Matterhorn has its unique, famous shape to it, because it wasn't necessarily cut out by wind and water erosion. It was instead sliced up into a nice little square cubical shape via a glacier. And fjords, you probably have heard those before. These are deep, steep I-sided inlets, I've never seen it spelled with an I, that are the result of glacial valleys. And again, this is a really big glacier doing this stuff, right? As glaciers melt, rocks and sediments in the glaciers are deposited. We call this deposition glacial drift. Glacial drift comes in two main ways, in till or in stratified drift. Glacial till is shown here as deposits the glacier melts and load of sediment is dropped. Very poorly sorted, large boulders down to fine clays, and it's because the glacier doesn't really care where it drops off. It just kind of drops it. You can know it's glacial till as opposed to something else because you can see, as shown down here in this image below, those scratch marks caused by the turbulence of the glacier. And, if this isn't a river initially or something like that. That's how you can get these erratic, gigantic boulders seemingly in the middle of no place. Again, if you are around the campuses, either Ironwood or Houghton, these things are common. These gigantic random, how the heck do they get their boulders? Well, a glacier dropped it off. And if you look at this image again, right, you can see the scratches. Landforms made by till. Moraine is an example of a landform made by glacial till. You can get lateral and medial moraines. A lateral moraine comes from the accumulation of debris on the side of the glacial till, and the medial moraine is created when two alpine glaciers converge. Here's an example of a medial moraine. We can see lateral and medial moraine shown in this example. And again, it comes from how the glaciers interacted with each other, because glaciers can be separate parts, right? Depends on wherever the head of the glacier is. The glaciers come down, meet in certain ways to create these cool-looking topography, cool-looking geologic features. End moraines and ground moraines, last two parts. An end moraine is the accumulation of debris at the terminus or the end of the glacier, similar to a conveyor belt, right? The glacier is going to spill all the sediment and stuff as it moves and drops. And your ground moraine is the rock-strewn plain created as the glacier retreats. Forms under the glacier backs up as it dropped all the stuff off, and the stuff's still there. You can see end moraines up here in the northeast, and these are the result of, this is the line of the glacier as it left, and it proceeded to form Long Island, Martha's Vineyard, Nantucket, Cape Cod, in the reason the geology of this area exists as it exists is because this is how far the glacier got. This is the end of the glacier, right? And we can see these moraines even better all over these parts. If we look at the extent of glaciers, and we can tell how far a glacier got by looking at the remains that glaciers leave. We tell the shapes of the glaciers, where the glaciers went, things of that nature. Notice the extent of the glaciers correlates to the locations where you find these moraines. Terrible picture of a moraine here. Sorry, I don't know how you're supposed to get much out of that. All right, let's talk a different type of glacial process, stratified drift. These are when sediments are laid down by glacial melt water. Notice water, not the glacier itself. Also called outwash. These sediments are sorted by size and weight of the particulates. It's stratified, essentially. We talked about stratification before. These are deposited, as I said, by the meltwater. Within these, you have outwash plains. These are glacial meltwater, as I said before, chocked full of sediments. Flows onto a flat surface, drops its load, builds a broad ramp-like surface, and creates braided streams. Right? So, you can see here an example of this. As the glaciers are retreating back, we have our moraines, as shown on the right side of this picture, but then you have this braided stream environment coming as the glacier retreats back, producing all these various effects that come about. Drumline fields, comets, etc. Right? Braided river, sometimes these are glacially related. Not always. Braided rivers can be tied to glaciers if need be. Other effects of Ice Age glaciers, crustal subsidence and rebound. We talked about this a bit with volcanoes, but glaciers are heavy, causes the crust to subside. When the glacier leaves, crust bounces back up. Sea level changes. Store a bunch of water as ice, it's no longer in the sea, causes sea levels to change. This is a issue that we are concerned about today with our modern climate change issues. As the glaciers melt, sea level rises. A lot of people live on sea level. Not a good thing, right? As shown here, during the last glacial maxima, about 18,000 years ago, sea level was nearly 100 meters lower than it is today. Since so much of the water was soaked up in glacier, you can see the outline of the U.S. and Mexico, and Canada, I guess technically, was much larger. The coastline was huge. Florida was a lot bigger, right? The Northeast carried on a lot further because, again, so much of that ocean water was sucked up into the glaciers. This causes changes to rivers and valleys, as you would expect, right? The advanced retreat of North America ice sheets changed the routes of many rivers. The map shows the Great Lakes and familiar present-day patterns of rivers. The coronary ice sheets played a major role in creating this pattern. B, we can see a reconstruction of drainage systems prior to the Ice Age. The patterns, as you can see here, is very different, and in fact, we don't have Great Lakes, right? Big difference there. You notice a lot of these tributaries are larger, more connected. The Missouri River was cut into two separate rivers, but the glaciers changed that stuff. And again, of course, created the Great Lakes. Glaciers were once more extensive than they are today. How do we know this? Well, we talked about this, right? Geologists look at modern glaciers and their deposits, then compare the modern deposits to other deposits around the world using the principle of uniformitarianism. If we see a glacier doing this now, and we look someplace else and see that same result, it goes to make sense that a glacier did it, right? Why would a glacier do this in one location, and then I find that exact same answer in another location? Why wouldn't a glacier be the cause, right? Glacier interglacial cycles occur about every 100,000 years. The northern hemisphere ice ages began between 2 to 3 million years ago, and the Antarctic ice sheet formed at least 30 million years ago. So we have one, the northern hemisphere ice age began between 2 to 3 million years ago during the Pleistocene epoch. Several advances or retreats of the glacier occurred, and then the Antarctic ice sheet created a long time before that. It's been around for a while. Here we can see an image of a reconstruction of the Pleistocene ice age, North Pole shown like that, and how far the ice actually reached during this time. Very large, right? So, what causes the onset of glacial conditions? Well, what caused the alternation between the glacial advance retreat and the Pleistocene? Good questions. Let's answer them. Possible causes of the glacial onset was plate tectonics, right? The continents were arranged differently than they were in the past, and this changed the ocean currents that distributed the heat. You also had changes in the Earth's atmosphere, changes in the reflectivity of the Earth's surface, and you could argue long-term solar fluctuations are to blame. I need to change the slide. I'm sorry, I missed that. I need to indent 2, 3, and 4 back so they appear more different. I apologize. But many different things. There's lots of different cycles and mechanisms at work in the Earth and in the different spheres, bio, geo, apno, and hydro. These all work together to create the environments that we live in. We can go over here real quick, the Milankovitch hypothesis, so if I mispronounce that takes into account the precession and shape of the Earth and the discussion of ice ages. The shape or eccentricity of Earth's orbit varies, right? I hope you're aware of this. We don't just follow a perfect circle. We ebb and flow back and forth. Likewise, the Earth's rotational axis also ebbs and flows back, sometimes by quite a bit. It wobbles around, it precesses around. Changes in climate over the past several 100,000 years can be closely associated with the variations as shown in these orbits and precessions. Of course, other factors are involved, but the further you get, the less sun that shows on a place where glaciers tend to occur. This promotes glacial growth. So, as I said countless times, and I can go over these individual questions. However, I do suggest you stop, pause the video, answer them as best as you can to make sure you understand what's going on. Because if you can do this stuff, you can do the homework, you can do the tests, you can do the labs, it all ties in, I would argue, very well. Just going to run through these. Don't have much else to say. Sorry about that. Again, I'm just giving you time to pause, answer these questions, then continue. Great Lakes formed during the Pleistocene glaciers. Let's talk about the Great Lakes a bit more. Well, I'm sure we're all familiar around here with the Great Lakes, right? Here are the different depths of the Great Lakes, this is a interesting way to look at it, right? I don't know if people are quite aware of exactly how deep Lake Superior is. It's massively deep. That being said, Lake Ontario digs in there pretty well too. But again, notice sea level differences here. So Lake Superior is a deeper lake by far than Lake Ontario, because even though they both dig into the earth similar amounts. Hope that makes sense. So the total height is much larger. Lake Superior's water level is up much higher than Lake Ontario's water level. That's why Lake Superior is so much deeper than, again, Lake Ontario. And why is that? Well, Niagara Falls a bit, right? As I said, Great Lakes look a certain way. They haven't always looked that way. So about 100,000 years ago, a glacier advanced from Canada over the region that we now call the Great Lakes. Over time, the ice moved over and carved out topographic lows, and then the glacial ice at that point was up to 2 kilometers, 2,000 meters thick. That much ice weighed millions of tons, right? That 2 kilometers of ice would be rather heavy, and literally pressed the North American continent downward into the Synestia. This is, again, a topic we've talked about before with mountains, but you get something stupid heavy like glaciers and mountains, they actually bend and buckle the plates, the crustal plates, as they exist. Over time, the climate began to warm about 20,000 years ago. The ice began to melt. Some of this melt water remained in these low-lying areas, the carved out, buckled down areas, to become the Great Lakes. So when the weight of the glacial ice was removed, North American landmass rose again to its position that had been before the glaciers impacted the area, but the glaciers also cut these parts out that stored the water. So you can see here, the glacier pushes forward, and at the ends of the glaciers, the water melts, creating these lakes, and it cuts all these divots out. The glacier eventually recedes back, leaving meltwater in, let's say, Lake Ontario there, or Lake Algonquin, as it was at that time. And then as it continued to proceed back and back and back, the water now had a place to sit and stay, which is why you get what you have shown there. So even 4,000 years ago, we had something that pretty close, looked like the Great Lakes region. These lakes create their own unique weather, lake effect precipitation. I'm sure you've heard of that if you live around the area, and rather moderate temperatures. Funny enough, the Great Lakes contain 20% of the world's fresh surface water. So very important monetarily for agriculture, for growth and development of civilization. The fact that all this fresh water exists in such an easy area. Lake Superior, as shown here, if again you live around the campuses in Gogebic, I'm sure know Lake Superior, contains by itself 10% of the world's fresh surface water. It is the second largest lake by volume in the world, and the largest freshwater lake by surface area in the world. So second biggest by volume, largest freshwater by surface area. It's cool looking, fun beaches. Highly suggest you go to it. Very cold a lot of the time, right? Lake Michigan, second deepest and third largest surface area lake in the world. A lot warmer than Lake Superior. Nextly, we get to Lake Huron, which has the same elevation as Lake Michigan. If you go across the Mackinac Bridge, there's no locks there, really. You can just drive right across it. That's the second largest Great Lake by surface area. So Lake Huron is actually larger than Lake Michigan, but smaller than Lake Superior. Keep track of it. Next, we get to Lake Erie, which is the shallowest and most polluted. What fun for it, due in a large part to the large amount of industrial cities that bank on it. And then we get Lake Ontario, which is downstream from the Niagara Falls. The other side of the Niagara Falls is Lake Ontario. And it is smaller than Lake Erie, surface area-wise, but also deeper, as we showed in that image before. And there's a brief overview of the lakes that are created by the glaciers that we have. Thank you for watching. I hope everything went well. You got any questions, leave them in the comments. I've said many multiple times over and over again. We keep saying it. And have a good day. Stay safe out there.